Hi, my name is Esther, and I'm going to be showing you how to do a redox reaction problem, and it's on page 910, and it's sample problem, well, it's actually not a simple problem, it's problem number 19.119. And the problem reads, oxalic acid, which is H2C2O4, is present in many plants and vegetables. Balance the following equation in acid solution, which that means we'll only have to go through 7 of the steps to balance half reactions since it is an acid solution. If it was a base solution, we'd have to go through 9 steps. So for part A, it gives you the equation MnO4 minus plus C2O4 2 minus goes to Mn2 plus CO2. So from the equation that was originally given to us, which was again the MnO4 minus plus C2O4 2 minus yields Mn2 plus CO2. So we're going to break this up into half reactions. So first we have MnO4 minus, and then we leave out the other part that's not related to the MnO4, and it just goes straight to Mn2 plus, and I'm going to leave some room so we have room to write everything else in. And then we also have the C2O4 2 minus going to CO2. Oh, I'm going to lose some more room. And that will go to CO2. Okay, now to balance these equations so we can later add them together, we've got to go through a series of 7 steps. And these are what we call the 7 simple steps for balancing a redox reaction. So the first step we've already done, we've broken up this equation into half reactions. So this is one half reaction, and this is another half reaction. And now it's time to balance all elements except for O and H. So in this first equation, we've already got, the O doesn't need to be balanced, so that's okay. We've got 1 Mn and 1 mole Mn, so that's good. Now we have, at the bottom, we have C2, so 2 of those, and just 1 C over here. So what we need to do is, let me get my notes organized. Add a 2 in front of the CO2. So now we have C2 and 2C, which is the same thing. Now the next step is to balance the O by adding H2O. So here we have O4. So that means that on this side, we need to add 4 H2O to give us those additional oxygens. And down here we have 4 oxygens, and we have 4 oxygens, so that's good. Now the next step, balance the hydrogens by adding H plus ions. Okay, so we have, on this side we have 8 hydrogens, and on this side we have 0 hydrogens, and we want those to be even. So we're going to add 8 hydrogens, and they have a plus charge. And down here, we don't need to add any hydrogens because we didn't add any waters, so we're already even for that part. Now the next step is to balance these charges by adding electrons, because in all of these, the balance on both sides aren't equal and they need to be equal. So we're going to do that by adding, on this side, the charges have summed up to 7, because positive 8 plus negative 1 is 7. And on this side, they add up to 2. So to get these to equal charges, I'm going to put a plus here, that makes it a little bit easier. We're going to add 5 electrons to this side, so 5e minus plus everything else. So now we have the plus 7 charge minus 5, that gives us 2, and on this side we have 2. Now for the bottom part, we have a negative 2 charge on this side, and we have 0 charge on this side. So what we need to do is add 2 electrons to this side to balance it up to have negative 2 on this side and negative 2 on this side. Now, there's just one more step left, actually 2, but so we have to get these electrons to equal each other so they can cancel each other out, because this one's on the left side, this electron's on the right side, and they need to be able to balance each other out. So what we're going to do is we're going to multiply the entire equation so these values add up. So we have 5 and 2, so the least common multiple of that would be 10. So I'm going to multiply the top one by 2. And then multiply the bottom one by 5. So now we're going to have 10 electrons on this side, we're going to have 10 electrons on this side, which is exactly what we want. So now once you go through and multiply that out, I'm going to take out these electron charges so I have more room. We have 10e minus plus 2 MnO4 minus plus 16H yields, now we still have to carry over this 2 Mn2 plus 2 times 4, 8 H2O. And we're going to do the same for the bottom. So we have 5 C2O4 2 minus, which goes to 5 times 2, 10 CO2 plus 10 E minus. Okay. So now we can cancel out what cancels out, and then we're going to add these two together so we have the final equation, which is what we're solving the problem for. So we have 10 electrons on this side, and we have 10 electrons on this side, and we can cancel those out because they're on opposite sides. And that's the only thing we can cancel out for this one because we don't have, say, a water on this side. If we had 1 water on this side, we could cancel it with these 8 waters and give us 7 waters on this side. So, once we cancel those out, we can add them together. Okay, so when I add these two together, this is what you'll get. So we have 2 MnO4 minus, and that's aqueous. That is not a Q. Aqueous plus 16H plus, which is also aqueous. And then we have plus 5 C2O4 2 minus, which is also aqueous. And I don't think I really touched on this earlier. What you do is everything that's on the left side, you add together and it stays on the left side. So we had the 2 MnO4 and the 16H plus. We had those already on the left side of the first equation, and we had the 5 C2O4 2 minus on the second equation on the left side. So we just added all those together into one. We're going to do the same thing for the right side. And I'm going to have to finish this on a second line because there's not enough room. So that leaves us with 2 Mn2 plus, which is also aqueous, plus 8 waters, and these are liquid, plus 10 CO2, and that's a gas. Alright, so that's the answer to problem 1. We've taken the half reactions and added them together, and that gave us the answer. Okay, so now the next part of the question asks us, if a 1.00 gram sample of plant matter requires 24 milliliters of a 0.0100 molar KMNO4 solution to reach the equivalence point, what is the percent by mass of H2C2O4 in the sample? So going back to percent by mass, the way we would solve this is we're looking for the mass of H2C2O4 divided by the total mass, which would be 1.00 grams, times 100, and that gives us the percent. So it starts off in the problem and it tells us that we have 24 milliliters. And we can't use milliliters, we have to convert it to liters. So if we do 24 milliliters and there's 1,000 milliliters per 1 liter, that'll give us 0.024 liters. So that's the value we're going to be using for the volume. So let me start using different colors so this doesn't get as confusing. We're going to take the 0.024 liters, and actually if we kept all the significant figures then it'd be 0.0240 liters. And we're going to times that by the molarity, which was, in the problem, 0.0100. 0.0100 molar. And then we're going to times it in our finished equation, which I'm going to go ahead and write that up here. We balanced everything out. We had 2MnO4 minus, and I'm going to leave off the states to save room because I don't know if I can fit everything, 16H plus 5 C2O4 2 minus gave us 2Mn 2 plus 8 H2O plus 10 CO2. Okay, so now we've got to look at the ratio between the C2O4 and then the MnO4. And even though in the problem it gave us KMnO4 and H2C2O4, those are still the values we look at to compare. So we have 5 moles, this marker's dying, 5 moles of the C2O4 2 minus, and then we have 2 moles of the MnO4 minus. And then we also need to times this by the grams per mole of the H2C2O4. So if you take the H2, write this out, we have H2C2O4. So we have the mass of this is 1.008 grams per mole, 2 of those, so times 2, plus 2 times 12.01, plus 4 times 16.0. That gives us 90.04 grams per mole. And we need to add that into the equation. So we're going to times it by the 90.04. And both of these right here have moles. So then, once we multiply that out, 0.0240 times 0.0100 times 5 divided by 2 times 90.04, that's going to give us 0.054024. And that's going to take us into the next step of the problem. Okay, so the last step of the problem is actually really easy. So we got this 0.054024, and now we're just going back to the original equation that I wrote up, which was the mass of the H2C2O4, which is this, divided by the 1.0 grams, which was the mass that was given in the problem. It said that if a 1.00 gram sample, so that's the overall mass. And then we just times that by 100. And this 0.054024 divided by 1 is just the same thing. Times 100, we just move the decimal place twice. And that gives us 5.40%. And that is our answer. Thank you for watching this video, and I hope I helped make it less confusing and not more confusing.